So this is supposed to be a course on complex analysis. So far, we've been talking really more about complex algebras, going over the basic properties of the complex numbers, but we really haven't put the analysis yet, in complex analysis yet. Which brings up the important question of what is analysis? Analysis is usually called one of the major branches of mathematics, along with things like abstract algebra and geometry and topology or things like that. And it of course has many different sub-branches. You got real, complex, functional, ordinary differential equations, harmonic, advanced calculus, partial differential equations, and so on. So there's lots of different ones, but what unites all of these things? And actually the first foray into analysis you've ever had is basic calculus. So we're going to consider 3 examples from basic calculus that are really going to give us the feel of what the entire spirit of analysis is, because it's a little bit complicated. It's not some easy definition I can just give you right now. So the first thing we can consider are power series. And the goal of a power series, or I guess maybe I shouldn't say power series specifically, I should maybe say infinite series, an infinite sum, is to add infinitely many numbers together. And you'll see a lot of these underlined words, pay attention to them. We're adding infinitely many numbers together. And so the typical example that's given is you have a guy, and he's a distance 1 from some wall or something, and he always measures the total distance he has left to go, and he always takes a step that takes him exactly halfway there. So if he was a distance of 1, meter away, then after he takes his first step, he's half a meter away. Then he's a fourth of a meter away. Then he's half of that, an eighth a meter away, and you guys get the point. Because he's only ever going halfway there, he never actually reaches the wall, but he keeps getting closer and closer and closer. So the first step he took was 1/2, then 1/4, then he took 1/8, then 1/16, and so if you add all of these up in an infinite sum, and here's the notation that you're used to, the sum of 1/2 to the n as n runs from 1 to infinity, then that should be, that should essentially take him to the wall. Infinitely many steps should take him the full distance to the wall, which was 1 originally. But how do we define this infinite sum rigorously? Because this is math now. Now's the time not to just compute things, now's the time to actually prove things rigorously in higher level math. And here's the big idea. Each finite sum is an approximation. There's another underlined word. I didn't mean to underline this word. Approximation to the infinite sum. So for example, if we call S1 just 1/2 by itself, which is written by this kind of silly sum notation here. I don't really need the sum here, but the sum is k runs from 1 to 1 of 1/2 to the a. And then you can define S2 to be 1/2 plus 1/4. So in general, Sn is going to be the sum of the first n terms of this infinite series. And so that can be written as the sum from k equals 1 to 2 of the same thing, 1/2 to the k. S3 would be the sum from k equals 1 to 3 of 1/2 to the k, would be the first 3. And in general, we would have Sn equal to the sum of the first n things, which is the sum as k runs from 1 to n of 1/2 to the k. This sequence, there's another underlined word, S sub n, is a sequence of approximations that converge to the number 1. There's another underlined word, right? You have a sequence of points. If they get closer and closer and closer to something, then we say that they converge to that number. And in this case, the sequence Sn, as I've defined it, this kind of n steps there without the infinitely many steps, it converges to the number 1. So we define the infinite sum to be the limit, the thing to which this sequence converges of this sequence. So that's the definition right there. The infinite sum is officially defined to be the limit as n runs to infinity of this sequence S sub n, which again is given by this formula here. Alright, so we can define infinite series by defining these finite sums. That gives us a sequence, asking whether or not it converges, and if it does, taking the limit, and that's what we call the infinite sum. We can play a similar game with derivatives. The problem now is that nonlinear functions are hard to work with, and he's crying, he's sad. But the idea that he gets with his little light bulb is that you can approximate them by linear ones. There's that word approximate again. Remember, approximation, approximate was one of the words I mentioned previously. So here's the typical picture that's drawn. You have this black nonlinear function f of x, and I've shown a best linear approximation here as this red line. It passes through the point a comma f of a on the function's graph. And so a would be the x coordinate of that, f of a, of course, would be the y coordinate there. And this will usually work as long as we pick a point, a comma f of a, on the graph, and we don't veer too far away from it. All right, this is a pretty decent approximation as long as we're close by. It's not so great an approximation over here and so on. So it's a pretty good local approximation, but not a very good global one. But of course, if we're going to do anything with this, we want to know what's the equation of this line. Well, we can use the point slope formula from algebra 1 or basic algebra, and we already have a point, right? We know that this line passes through the point a comma f of a. So all we need now is the slope. What's the slope? So how are we going to figure out the slope? Well, a tangent line is like a secant line whose 2 points are infinitely close. So there's the word infinity again, or infinitely, some version of it. So first of all, what do I mean by a secant line? If a tangent line is something which kind of hits the graph at one point and hugs it as closely as possible, a secant line is something which hugs the graph at 2 points. Let me switch colors here to gray. So consider this blue line, for example, here. It passes through the point we're interested in, a comma f of a, but it also hits the graph at some other point, the x-coordinate of which is not a, but a plus h1, right? You've added something to a. And so the slope of this blue secant line, secant means that it hits it twice, the slope of that is given by the change in y over the change in x. Well, the change in x from a to a plus h1 is just h1. And the change in y is, well, whatever its value at a plus h1 is, minus whatever its value of a is, f of a plus 1. Then you can pick an a plus h2, an h2 that's even smaller than h1, so that gets us even closer. So then this green line, which has this point, and which of course goes through that same original point. And it has a secant line given by a similar formula, except h1 is replaced with h2. And the point is that the sequence we're interested in here is a plus hn, something just a little bit to the right of of a, where the hn's go to 0. So as n goes to infinity, this is getting closer and closer to our original point a. And that's kind of what I mean when I say that a tangent line is like a secant line whose 2 points are infinitely close. We're taking this second point of these secant lines and we're letting it run closer and closer to this original red point. So you can think of a tangent line as having, those 2 points which it passes through coinciding. They're kind of infinitely close with each other. So the point is that the slopes of the secant lines form an approximation, there's that word again, to the tangent line. Your goal is to form a sequence of secant lines whose slopes converge, there's that word again, to some limit, and that limit is the slope of the tangent line we're interested in. So the slope goes by the name of derivative here, the derivative of f at a, and it's given by this formula. The limit, as n runs to infinity of, these are the formulas we had for the slopes of the tangent lines, f of a plus hn minus f of a over hn. And this may not be the formula as quite as you remember it. You might have remembered something like the limit as h runs to 0 of this, which looks similar and is essentially the same. As n runs to infinity, remember these h sub n's form a sequence that's going to 0. So this thing on bottom is going to 0 by either way, and this h is going to 0 and this hn is going to 0 and so on. So it works the same way. So we can play another similar game with integration. The goal here is to find the area under a graph and above the x-axis, and for example from some a to some b, like this, right? We're interested in that area there. And the idea, again, pay attention to these underlined words, is to approximate it with rectangles. The true area will be a sum of kind of infinitely many, infinitesimally thin rectangles. Let me show you the picture of that. Right there. That's the picture. Infinitely many, infinitely thin rectangles. But of course, the natural thing is to find these finite approximations first. form a sequence of them, or a sequence of the areas that they would give you. Again, the area we're looking at is the sum of the areas of these rectangles, and the limit of that sequence should equal the true area that we're after. Alright, so here's a little picture of it. There's this, maybe the second term in the sequence, 2 rectangles. Third term, these are left-hand Riemann sums, if you remember that from basic calculus. And the limit of these left-hand sums as n runs to infinity is, well, here's the more formal formula of it if you wanted to actually write it all out. And that's what we define the integral to be. Alright, so there's a pattern in each of these 3 examples, and it's the pattern that really represents the spirit of what analysis is. You have something complicated, and usually it involves infinity in some way. So here we wanted to have this kind of infinite number of rectangles, infinitely precise area, or here we kind of wanted a secant line. We wanted to find the slope of a secant line that had the 2 points infinitely close together, or we wanted kind of an infinite approximation to the nonlinear function. Here we wanted to sum infinitely many terms. So there's usually something complicated. Oftentimes it involves infinity. And your goal is to form a sequence of simpler things. So if those were infinity and that's why they were complicated, then this will usually be finite in some way. Simpler approximations to that complicated object. So simpler things which are kind of approximations to that complicated object, and the point of this sequence is that it should be a better and better approximation with each passing term in the sequence. So if your complicated object is S, and you have a sequence of simpler objects S sub n, then you kind of want them to converge to S by becoming better and better approximations, and that's the point. You ask that that sequence of approximations converges to a limit, and that in fact that limit to which it converges is your original complicated object. So the 3 examples that we just saw use this approach to define things, right? We would define what it means to take an infinite sum, or the derivative, or an integral. But it can also be used, and it is used in analysis, to prove theorems. So the approach there is to prove that a complicated object, and I know I'm being very vague about what this actually is because it applies in so many different contexts. So you have some complicated object, and it has a certain property. You want to prove that it has that property by first approximating it, there's that word again, by simpler objects. Then showing that each of the simpler objects have the property that you're interested in, which should presumably be easier because they're simpler. And then finally showing that anytime you have a sequence of things with that property, and it converges to some limit, then the limit also has that property. So if we have a sequence of simpler objects that all have that property that converge to our more complicated object, and we've shown that this property is preserved under limits, well then we've shown that our more complicated object has this property. And so these are the words that are kind of floating around. You have approximations, sequences of approximations. You want to take limits of them, so you want them to converge, and usually there's infinity involved, which is what's making which is what's making things complicated in the first place. And so all of these words really drive at the spirit of what analysis is. This whole game that I have written here at the bottom, that's analysis. And that's the spirit of every different one of the branches of analysis, really. So in order to move forward and rigorously work with analysis, we're going to have to address certain questions. Like, a sequence. Well, a sequence is a simple thing, right? If S is just a set, and it could be any old set, okay? It can be a set of any kind of object. A sequence is just an infinite string of elements of that set. And there can be repeats if you want there to be repeats. That shouldn't matter. And it just goes on. It's just some infinite string of elements of that set. And for those of you who know a little bit more about set theory or something, really what we're talking about is a mapping from the natural numbers 0, 1, 2, 3, and so on into your set S. So a sequence is a silly thing to consider. It's not very interesting if S is an arbitrary set. What we want is to have some notion of this idea that a sequence can converge in a given set. So you can't do that with an arbitrary set. You have to kind of worry about how do we define convergence of sequences in our set. Usually we have to impose some extra structure. So this video is pretty general. It's driving at what is analysis. So this isn't just going to be used in my complex analysis videos. It's going to be used in probably many more videos to come. Any kind of analysis videos. So we're always going to have to worry about this question of what precisely convergence and limits of a sequence in our set is. So for complex analysis specifically, the set we're talking about is the complex numbers. So in the next video, we're going to talk about what is a sequence of complex numbers, and more importantly, what does it mean for a sequence of complex numbers to converge, and what does it mean to take limits of such things. Once we're done with that, then we can really start to do complex analysis.